I think in last class we started talking about convolutional neural network. We said instead of having a flat input or flattened input, like a vector, we might have some input that there is some spatial relationship between these elements. Like, for example, there is a number here, for example. And you want to find those relationships to detect something. Like, for example, you want to read these numbers or alphabet or whatever pictures, understand it, and find those a spatial relationship and transfer it to the higher levels. Why transfer it to higher levels? To detect more advanced connections. Like, for example, first find edges and then find, for example, I don't know, lines or shapes and then objects at the end. So we said normally feed-forward neural network or dense neural network is not very good way to detect two-dimensional picture or three-dimensional. It's not just pictures. Even LiDAR, for example, can give you lots of information that like a three-dimensional. It's like an image actually, but not exactly. But you can consider that as a three-dimensional input that is good to use maybe convolutional neural network for that as well. Because there is some spatial, anytime you have some spatial relationship between data, you can use convolutional neural network. So we started with that, and we said, okay, so convolution is the best operation, then can do that. And we started talking about convolution operation, how that works. And we don't know how much we talked, but today we want to again continue convolutional neural network more, maybe deeper, and especially see if you want to design a convolutional neural network for one system, what is the steps? So today we're going to see steps. How many steps we need to actually define a convolutional neural networks. For example, we need some convolution layers. And then imagine this is an image. Oh, thank you. Imagine we have image, and we have, for the first layer, for example, we use 3 kernels. Each kernel detects some low-level features like lanes, corners, edges, whatever. And corresponding to each kernel, we make one output. This output is almost same size as image, maybe a little less. Based off the size of the kernel, you can find that. And then, because this, we call this feature maps. So based off the number of kernels, you're going to have different feature maps. And because the size is still this big, we do another operation. We call that pooling. We make these feature maps smaller, like half, for example. This is called pooling. Or for example, if you use max, it's going to be max pooling. When we do that, this step can be repeated many times. One for low-level features and then for higher-level features, moving from, for example, edges, go to, for example, objects, for example. Okay, so we repeat this step, but at the end we have lots of, after max pooling, we have lots of like small images. It still is not classified. So what we need to do, we need to give that to, first of all, we need to flat this information, like put them in a vector, flattening. After flattening, we use normal, a dense neural network that we had before. Dense. For example, here we have two-layer dense. Dense means everything connected to everything. And finally, we do actually find the likelihood of belonging to, right here, finding likelihood of classes. At the end, we are still finding likelihood of the class belonging to those classes. So this is the general steps that we need. And we want to talk about each part separately. So again, I'm going to explain these parts. First is convolution, pooling, maybe flattening is not considered. Flattening and dense is the last part. This can also call classifier. It's like normal classifier. And this convolution and pooling can repeat it so many times, like maybe so many times, maybe a couple of times. This is a structure of CNN. That's it. So the size of kernels specify these features that you want to take out, and a number of layers showing how advanced this combination is gonna be. It's, you know, those objects, how complex are those objects? We can see practical examples, like one example for detecting handwriting numbers, and one for image processing. We can see that today. Okay, this is just I want to just set up the stage for today's class. This is what we're going to talk today. These are steps. Okay, let's get started with this architecture. So as I explained, we have convolution layer, we have activation function. Oh, I forgot to mention that part. Activation is another part to adding nonlinearity and pooling. These three can repeat it. These three parts can repeat it many times. It depends how complex is your final image. How complex is your final image? When I'm saying how complex is your final image means connection between these patterns makes at the end the object. Okay, so this is repeating, and at the end we still have fully connected layer. Why we need fully connected layer? Because we want to get likelihood of belonging to those classes. Again, we need to find that part. So the picture is like this. As you can see, we have input, we have multiple kernels, and these kernels are actually sliding across the image and make feature maps for each. For example, here we had 3 kernels or 3 filters. We call them filters too. So we find 3 feature maps and then shrink these feature maps to a smaller part using max pooling. Why we are doing that? We want to make it simpler. And max pooling is still gonna keep this relationship, this spatial relationship, gonna stay after max pooling. We assume, we assume that's gonna stay. And then we do flattening. Why we do flattening? Flattening means if you have, for example, a matrix, put all the lines in a vector, in a big vector. That's called flattening. Flattening means like make it flat as a vector. So 2-dimensional gonna be 1-dimensional. We can do that. And then use normal dense neural network, like 2 layers, 3 layers, it depends. Some application, even 1 layer is enough. Where we put this activation function, this nonlinearity, actually nonlinearity happening in this convolution. So here we add activation as well. You're going to see that in next slide, nicer. Okay, so this is the process that we're going to explain. Convolution layer and activation most of the time, for example, in TensorFlow, happening with 1 instruction. 1 instruction has both of these 2 at the same time. Do convolution and do activation. Let's make this picture a little bigger. Here is very small. Okay, as you can see here, this is 3-dimensional image. When it's colorful, you have 3-dimensional image. So for this 3-dimensional image, this is the filter, and the filter are those parameters that we want to learn. Actually, in convolutional neural network, we learn features. We learn kernels. We learn these values in kernels. And as you can see here, we do activation function. Most of the time, ReLU, however, here is sigmoid or tangent. Is it tangent? I don't know. It looks like tangent. This is under, yeah. But anyway, any activation function. So before making the output for like feature map, this is the feature map. We do activation as well. Okay. So the output of the feature map is after activation. So all of this can happen with 1 instruction in Python, and we can see that. Let's come back. Okay, so, and last class we also explained that how this convolutional mathematically works. Instead of having dot product that we had it in dense neural network, we have like weighted sum. We weight some, but this weighted sum exactly is like how convolution is. So the how convolution works. So this is the formula for convolution. We add it by with a bias value, and then the result gonna go to the function of activation, like ReLU, to get some nonlinearity, and then make feature vectors. So we make different feature maps. We make different feature maps based off different kernels. So that's a kernel. If you have, for example, 3 kernels, you're going to have 3 feature maps. And these feature maps are the output of passing by activation function like relu or tangent, or yeah, that's a process. So here I explain what is this convolution formula. You know that before. So X is just input. It's showing how it's sliding, how we can slide the kernel across the image. So this is how it works. So normally this is kernel W, and the image is any point in image QP. It's going to multiply with each point like what it's called position wise. Each position of the image going to multiply with that and add up together, and plus bias going to make a new value. Okay, so we talked about that last class. So this is convolution layer, but convolution layer also has nonlinearity part. Nonlinearity part coming from one of those activation functions, mostly ReLU, rectified linear unit. Without ReLU, a deep convolutional neural network just acting like a big linear transformation. It's not doing anything advanced. So ReLU function actually makes it nonlinear. How ReLU function works, as you can see in that ReLU diagram, is simply takes any negative values and set them to 0. So the negative values, look at this picture. In this picture, you can see those black, darker values are actually negative values. They get to 0. And the white parts, the bright parts, are positive values that stay. So this is how ReLU acts. But as I mentioned, in Python, mostly you use Keras API, and in Keras API, both of these happening with one instruction. This is the instruction that you can use. Convolution 2-dimension, 36, showing the number of actually neurons. We call them neurons, or filter. Actually, a number of filters or kernels. Number of kernels. And this is the size of kernel. And this is the activation function, ReLU. Doesn't need to explain. Activation function. So this convolution 2D doing all of that at the same time. Any question about this? Okay, so that part is the main part of convolution neural network. Convolution and adding nonlinearity. Adding nonlinearity and convolution are going together with one instruction. And then we need to sort of make the feature map a little smaller, because feature map normally is the same size of data. It's not exactly the same, a little smaller, but it still is not small enough. So most of the time we do pooling or max pooling. Max pooling, we're going to explain how that works. So what max pooling doing, reduce this spatial size, reduce the size of these feature maps. But it's going to keep the important information. Even though it's minimized, it still keep the info. How we can keep the information? Because most of important informations are in highest values. So if we keep those highest values, we still have those information. So that's why max is for that. So typically we use a small window, mostly 2 by 2, and slide that window across the feature map, like what we were doing with convolution, but the operation here is different. Operation is not convolution, it's maximization. It's just maximize. We just find the max, nothing more. So we find the max. What else I can say about that? Oh, let's see the picture. So for example, in this picture, you can see we are sliding this matrix 2 by 2. This is we are considering the size of max pool is 2 by 2. So we start first consider this. What is the maximum of it? 6. So we write 6 here. And then move that 2. Why 2? Because we said strides are 2. A stride showing how we move forward, how a step we go. Normally in convolution, a stride was 1 because we wanted each pixel separately find the convolution. But here can be 2. It can be 1 too. If be 1, the result going to be different. Let's do it for 1 in this example to see how it works for 1. If a stride is 1, okay, so let's see what's happening. The size of the pool still is 2, okay, the size of a pool is still 2, but the stride is 1, so it means we move 1 by 1. First, so the result gonna be 3 by 3 this time. How we find it? First, find this one. We want to find this one. So because the size is 2, we consider this, and the max is 6. So 6 gonna go here, and then we go one step because the stride is 1. We move 1. Find the max. The max is 7, and move it again. 1 step. So step by step move that, and the max is 8 here, and then move this, for example, here. The max is 6. Then I put another colors to don't mix too much. And then this one, the max is 7, and so forth. I'm not gonna continue because it's gonna get messed. But you got the idea. So this is how we find the max pool. The max pool function working like that. It can work step by step, or 2 step by 2 step. You know. Okay. Any question about that? It's easy. It's nothing complex. Let's clean this up. So that's max pooling, and max pooling gonna decrease the size of the feature map, but at the same time, it still keep that a spatial relationship. Because I said, I explained why, because most of important parts are in highest values. If we get the max, they're gonna survive, they're gonna stay. The point is to keep these relationships in the higher layers. We want to keep those relationships, these information to the higher levels. Or lower levels, maybe, lower levels. Next layers, actually. Okay, so this is again explaining that, nothing more. Okay, so another thing that's happening in max pooling is that translation invariant that I mentioned. Translation invariant means small changes in objects or in patterns that still can get detected. is not gonna change a lot. Small shifts in input don't change the output that much. So the max pooling actually let that happen and let that translation invariant happen. Okay, so this is the example that we already explained for that. Max pooling has one instruction in Keras, TensorFlow. In Keras API, we have like a function called max pooling 2D that you give the size of the size of the pool and size of a stride. If you don't give the size of a stride, most of the time consider same size. If the size of the pool is 2 by 2, it's considered that also 2. Okay. Okay, so that's it. Let's go for general structure of CNN. So in this picture, you can see exactly what's happening. If you have an image, input is a three-dimensional image. So we have multiple kernels, this depth coming from these multiple kernels. Okay, multiple kernels, and each kernel detects some characteristic of image. For example, edges or corners. And we do pooling. So this part is the first layer. We do pooling, however, here we do nonlinearity as well. However, nonlinearity happening actually in here. We do nonlinearity as well. That sigma that I mentioned is an activation function. Maybe I just write activation. Activation. So activation happening in a convolution layer. So it actually mentioned here ReLU. A convolution and ReLU happening here. And then we do pooling. This is one layer. And then we do the same, not same, I mean, it different kernels for sure, different method of shrinking or pooling can be different. It's not always same, but it's repeating. Every time that is repeating, we are making more actually advanced in pictures. Like for example, here is edges, here is shapes, for example, and here is objects if you have more. Okay, and more. However, it's just 2 right now, so it doesn't have this part. Okay, now it's time to flattening. We do flattening. We make those shrink two-dimensional picture. They are still 2-dimensional, but multiple of them. We make them one vector. We make them one vector. This is called flattening. After flattening, the rest is just normal dense neural network that I already explained as well. And as you can see, is dense. Every neuron connected to every other neuron to the next layer, and depends on number of layers. Going at the end is going to give you using softmax to give you likelihood. Softmax give you likelihood of belonging to those classes. Give you likelihood. Likelihoods of belonging to, for example, for this shape is a car, so probably for the car you have, I don't know, 80%, and for truck is, I don't know, 1%, for van is, I don't know, less, and sum up to 1. If you add them all together, it's going to be 1 because it's probability, and that's how softmax do normalization. Remember, in softmax we do normalization to add up to 1 because it's probability need to add up to 1. So this is the general steps that happening in convolutional neural networks. So you, as a robotic engineer, you need to define this part. Most of the time, you need to define how many layers you need and how this structure works. For example, you need to see how many kernel you need. You need to find how many kernel you need. You need to find how many levels you need for neural network. And also, you need to see how many dense layer for dense network. You need to consider this thing, nothing more, you know? So it's not that complicated. Every other part is gonna be done automatically. And even you can sometimes do based off validation, because this stuff are considered the variables that you can use validation data to find them. And you can find the number of layers, number of kernels, size of kernels, and you can tune them based on validation data. They are hyperparameters. They consider hyperparameters. Any question about this part? So I think you got general idea of how CNN works. Let's see some practical example of that. One of the very nice example is actually this handwriting program that you can write something and it detected, for example, a number between 0 to 9, 10 digits. So in this one, the structure is like that. We just have two layers. I'm just gonna go directly to the code because we don't have time. In this example, there is a prepared data set called MNIST. This MNIST already has lots of labeled handwriting data. If you go there, there is, I don't know how many, but there are a lot. So in this code, we use those data set. We read them, and they are labeled. We divide them to train and test. We could take validation too, but we didn't. But normally we do that. Why we need that? To find those hyperparameters. And I told you what these hyperparameters means. The size of the layers and the kernels and those things. You can tune them as well. Anyway, here we have two layers. We can define neural network in two different ways. In last slide, let's go back to the last slide very fast. In last slide, as you can see, we defined layers with this function, layer 2D, and this is get the input, activation, number of kernel, size of the kernel, and then in a next layer, we do, because they are all layers, max pooling, and then layers convolution, layers max pooling again, flattening, and 128 dense layer to detect, for example, at the end, you do softmax and 10. This 10 coming from the 10 digit at the end. So this is one way you can write that. The other way is to find X and give X as an input to the next layer. They both same. If you use a class like this class, sequential model like this is a class, or use X and feed the X to the next layer, both same. You can use it in two different ways. Okay, here we use this feeding way. So we made input here. So input is just normal 28 by 28 pictures. This is for training part. And then this is not for training, it's for both training and testing. So this is the structure of neural network. So structure, the input is 28 by 28 pictures. We give this input to first layer is convolution, 32 3 by 3 kernels, ReLU activation. We give the result to the 2 by 2 pooling, and then result of that going to another layer, this time 64 kernels, 3 by 3 again ReLU, and we are done here. Even we didn't do max pooling in this part, and we give the result directly. We flatten and give that to dense neural network, 64 neuron ReLU, and we give that to another dense, two-layer dense, and this last dense is just softmax, and the result is 10 digits, and it works. I tested. So if you run the, however, it has some parts to write with mouse. You can write the a number. I tested, for example, 8 here. As you can see, here detected 8. Is 8 coming from that? And here, for example, I wrote 4. I wrote it fast with mouse, so to make some noises, but I still could detect it. However, it's not always correct, but it's enough. It's good enough to detect that. And how many lines? It's less than, I don't know, maybe 30 lines, because I removed some parts related to mouse, and so I just show the main part. And it works amazing. So this is how in practice you can use CNN. But this example was very famous example. But based off your application, you can use neural network in so many different ways. You just need to think, for example, if you want to solve something, okay, I make this problem as a CNN problem and try to solve it. This can give you idea for your last project as well, because you need to use, it's not have to, but it's better to use convolutional neural network for that as well. Okay, another example, last one, is real 3-dimension image, like colorful image. So in this is another data set that exists. This data set called CFAR10. CFAR10 is coming from the classes. It has 10 classes: animals, trucks, cars, I don't know, sheep, birds, automobile, and they are 10 groups anyway. And this, again, easily, you don't need to do lots of work. This is all the classes: airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, truck. And then we make 2-layer neural network, the convolution neural network, one 32 and another one 64 kernels. Both has max pooling, and actually 3 neural network, and then flatten that and give it to just one dense neural network. The last one is just softmax. That's it. And as you can see, softmax makes 10 output, and each of them is just probability of belonging to one of those 10 classes. And it works too. I tested this as well. So this is the testing result. However, it's not very precise, but even we as a human, if we see this picture, we can detect what is this. Can you? I couldn't. It's a horse, for example, but you can't even as a human that you are, after this much training, years and years evolution, still you are not able to detect that. But it didn't detect bat, it detect deer, but it's horse. And for but the frog is a little not good, but this is also horse, but it's still not bad. But this one is cat, but it detected airplane, probably because of the window behind. But this is for very low resolution pictures. Imagine those pictures are higher resolution. So it just depends on the number of layers and your computer, how strong is that. It can detect them amazing. Okay, any question? Oh, here we also have validation accuracy that showing, for training accuracy and validation accuracy that they are converging. So it means it works. It means it works. Anything else I want to mention in this code? The rest is, there is another. No, the main part is here, defining the model happening in this part. The rest is just showing the output. Oh, okay, something that I forgot to mention is after defining the model, you need to compile the model. So the compiling the model is the training part. Compiling the model happening with the function compile in TensorFlow, in Keras actually, because TensorFlow is just a library, it's very low-level library. And there is so many API that works with TensorFlow. One of them is Keras, that is very simple. This Keras is very simple. The functions are from Keras. Anyway, compile is for compiling the model. Adam is the name of optimization method. It's like gradient descent is a variation of that. And last function is cross-tropy, as we can see. It's called a sparse categorical cross-tropy, but it's similar to cross-tropy. And the metric is accuracy that we explained before. And then after compiling, we need to fit it. To fit that, we need training data, because it's X and Y, training data X and Y, and the number of epochs. And the number of epochs is just 5, it's nothing. You can make that more even. And validation data is just for validation, based off this accuracy to find that. And that's it. That's it. And they collect the history. In the next picture, let's explain that as well. And what else we are, and we do evaluation here. And this evaluation, we do this model. We already learned the model. Everything is in that class model. Based off this test, we find loss for test to just draw this one. That's it. Okay, I think we are moving one step forward. We are done with neural network. Now, next class, we're going to start other sensors. We're going to work in other type of sensors, especially LiDAR. We're going to focus in LiDAR and the rest of the camera. Okay, any questions? Any questions? Okay.